Hello, I'm Felix and today I'm interviewing the James Webb Space Telescope lead ground systems engineer. Is that correct?
That's correct.
He also happens to be my brother, Francis. So Francis, tell us, what is the James Webb Space Telescope?
Well, the JWST, or the James Webb Space Telescope, is really the successor of the Hubble Space Telescope, is what I usually tell people, because most people recognize the Hubble that launched in the, over 25 years ago now.
So it's a successor to Hubble. What are the differences?
Well, the main difference is Hubble, with all the pretty pictures, it has pretty pictures because it takes images in visible light, like our eyes see. There's limitations with that. Being the successor, JWST, or the James Webb Space Telescope, is going to take images in near-infrared and mid-infrared ranges. That allows us to go further back in time.
Because you can see through dust.
Correct.
And other such things. It just looks right through it at those frequencies. So
that's the one reason. And the other reason is with the Doppler shift, as the universe is expanding, the galaxies we want to look at are actually moving farther away from us. And as things move farther away, they shift from the visible light or ultraviolet light to infrared light.
Okay, Francis, so that Doppler effect, where your images that would otherwise be invisible in the visible are now visible in the infrared.
Correct. The best analogy, thank you, is
I'm his older brother.
Is a train. When a train's coming at you, you hear it at a different pitch than when the train is going away from you. And that is because when the train is coming near you, the waves are being compressed, raising the pitch. And as the train's leaving, going away from you, the waves are extended and it lowers the pitch. Same thing with the light, where it's blue if it's coming at you and it's red if it's going away from you.
And how does this help you see images that you wouldn't otherwise see?
We're going so far back in time. We're going to 250 million years after the Big Bang. The universe is 13.7 billion years, so we're going to like 13.5 billion years in our past. And you could only do that in infrared. The Hubble stopped short of that because it could only see things in visible light.
Okay, and
because of the Doppler shift, with everything shifting away from us, the wavelengths have changed over the 13-some billion years.
They've shifted that much?
Yes.
Yeah. Okay. So as most people know, Hubble is in a low orbit because the space shuttle went and fixed it several times and things like this. Where is JWST going to be located? Okay.
For several reasons, JWST cannot be at low Earth orbit. We can't be serviced by astronauts. It's going to be at the L2, or the Lagrange point number 2 location in the Sun-Earth system.
That's far.
It's about 1 million miles away, or 1.5 million kilometers away.
As opposed to Hubble is 200 miles?
300.
Okay.
Yeah. And the main reason for us going out there is being infrared. Infrared is heat. Anything gives off heat. We want to be far away enough from the sun and the earth to cut down at any light or heat from the sun and the earth.
Okay, that would contaminate the viewing, essentially.
Yes. Yeah, exactly. And L2 is designed, you have the sun, you have the earth, and then you have where JWST be in a straight line. We have a sun shield that's about the size of a tennis court that will block the sun, light, and the earth heat from the cold optics and cold detectors we have on the observatory.
Okay, and those detectors need to be cold in order to operate properly on the spacecraft.
To be able to pick up the very, very faint images, that we're going to be looking at light that's 10 to 100 times fainter than what Hubble sees.
Okay, great. So what is it that your department does for James Webb?
Okay, so a little background. James Webb is managed out of the Goddard Space Flight Center, the NASA Center in Maryland. I'm in the Ground Segment and Operations Department. My job is to lead ground system engineers to make sure all the puzzles on the ground system work together.
And by ground system, you mean the guys that are going to be operating the spacecraft once it's in orbit?
That's one piece of the puzzle. It's from the network, the giant dishes we have to communicate with the spacecraft, to the control center, to the scientists that finally get their data. My job is really to make sure to put all those pieces together, that everything communicates properly.
Okay. Okay. So Francis, tell me a little bit about these components of the ground segment.
Okay, so there's several key major components we have to be able to communicate with the observatory. Working from left coast to right coast, we have the Deep Space Network that's just up the road in Pasadena, California, managed out of the Jet Propulsion Laboratory.
And those are big dishes that communicate.
They have dishes all over the world, in Goldstone, California, Madrid, Spain, and Canberra, Australia. We use their 34-meter antennas to talk to the James Webb. We need something that big because we're so far out in orbit. So the commands go from there to the observatory, or the data and telemetry come from the observatory to there. And they're sent to our control center, which will be at the Space Telescope Science Institute on the campus of the Johns Hopkins University in Baltimore, Maryland.
So these signals are going everywhere.
Yes, yes. And at the control center in Maryland is where we'll do health and safety checks, send the commands, do all the science planning for the observatory, and do all the data crunching to actually create the science products for the scientists.
How many?
It'll be quite the number.
Now, as a planetary scientist, I know, it's not just the deep space astronomers that are looking forward to James Webb. Planetary scientists are looking forward to it as well. All these planets that they're finding now around distant stars, they'll be able to look through the atmosphere. Stars in the background that occult through the atmosphere, you'll be able to tell what is in the atmosphere. Because you can measure the star, then when it goes through the atmosphere, you can subtract out what the star has, see what's in the atmosphere. You can look for biosignatures, that's life. So, and they're already working all the plans for this, so can't wait.
Right, very exciting.
Yeah. Okay, yeah, I'm not going to turn the mic this way.